Have you ever, looked at a straw in a glass of water and it just looks broken or bent?
Yeah, it takes that weird little turn at the water line.
Exactly. It seems like magic, but it's actually about how light travels, or rather how its speed changes. Think about this. In empty space, light is incredibly fast, like $3 10 meters per second.
The universal speed limit, basically.
Right. But then put it in water and it slows down considerably to about $2.25 times 10 meters per second.
And even more in something like glass, maybe around 2 times 10 meters per second.
So today on the deep dive, we're getting into why that change in speed makes your straw look wonky and causes all sorts of other, well, really interesting visual effects.
It's a great topic. That simple observation, the straw, it really opens the door to understanding how light interacts with, well, everything transparent around us.
Mm.
And for this deep dive, we've looked at some really good materials explaining refraction. That's the key term here. It's all about light changing direction when it goes from one thing to another.
Perfect. Yeah, we've got some solid sources, and our mission today is pretty straightforward. Figure out what refraction is, why it happens, and see some cool real-world examples, but, without needing a physics degree to follow along.
Sounds good. Let's dive in.
Okay, so first things first. What is refraction at its core?
Okay, so refraction is essentially the bending of a light ray. It happens when light moves from one clear material, say air, into another clear material like water or glass.
Right at the boundary.
Exactly, right at the surface, the interface between the two. That's where the bend happens.
Okay.
Now, to picture it, imagine a beam of light hitting that surface. That's your incident ray.
Incident ray. Got it.
As soon as it crosses into the new material, it changes direction. That new path is the refracted ray.
Refracted ray.
And
Oh,
there's one more piece, an imaginary line. Draw a line straight up, perpendicular to the surface, right where the light hits. We call that the normal.
the normal, like 90 degrees to the surface.
Precisely. Now, the angle between the incoming light, the incident ray, and that normal line, that's the angle of incidence. We usually call it I.
I for incidence. Okay.
And the angle between the light ray after it bends, the refracted ray, and that same normal line, that's the angle of refraction R.
R for refraction. Okay, incident ray, refracted ray, normal line, angle I, angle R. So why the bend? Why doesn't it just go straight?
That comes back to the speed change we mentioned. Some materials make light slow down more than others. We call a material optically denser if light travels slower in it.
Like water or glass compared to air.
Exactly. Air is optically rarer. Water and grass are optically denser. Now here's a rule. When light goes from a rarer medium, like air, into a denser one, like water,
It slows down.
it slows down, and because of that, it bends towards the normal line.
Towards the normal. So angle R would be smaller than angle I.
You got it. Angle R is less than angle I in that case.
Okay, so what about the opposite? Light coming out of the water, back into the air, denser to rarer.
Then the opposite happens. Light speeds up as it enters the rarer medium, the air. And because it's speeding up, it bends away from the normal line. Away from the normal. Yeah. Meaning angle R would now be bigger than angle I. Precisely. Angle R is greater than angle I when going from denser to rarer.
So it's all about hitting that boundary and either slowing down or speeding up.
That actually makes a lot of sense. Is there any time it doesn't bend, like goes straight through?
Yes, one special case. If the light ray hits the surface exactly head-on, perpendicular, right along the normal line itself.
So angle I is 0.
Exactly. If the angle of incidence is 0, the light just goes straight through without bending. The angle of refraction, R, is also 0. No deviation at all.
Huh. Okay, interesting. So let's go back to that bent straw or stick or whatever. Can we piece that puzzle together now?
Absolutely. Think about the part of the stick under the water.
Okay. It's in the denser medium.
Right. Light rays are coming off that submerged part of the stick, traveling through the water towards the surface.
When those rays hit the surface and go into the air, the rarer medium happens.
They speed up and bend away from the normal.
Exactly. They bend away. Now, your eye sees those rays coming from the air. And your brain, well, it assumes light always travels in straight lines. It doesn't know about the bend.
Ah, okay.
So your brain traces those bent rays back in a straight line to figure out where they seem to be coming from. And because the rays bent away from the normal, that apparent source point looks higher up than the actual stick.
So the part underwater looks shallower and bent at the surface?
Precisely. It appears raised, and consequently the stick looks bent right where it enters the water. Only the submerged part looks shifted, of course.
Wow. That's a really neat explanation. It's like a little optical illusion created by the light changing speed. And didn't the source material mention something similar with a coin in water?
Yes, exactly the same principle. If you put a coin at the bottom of a cup and fill it with water, the coin looks closer to the surface than it really is.
Same reason. Light from the coin bends away from the normal as it leaves the water.
You've got it. Light rays from the coin travel from water, denser, to air, rarer, bend away from the normal, and your brain traces them back to a shallower apparent position. It creates a virtual image of the coin that's higher up.
Okay, so these everyday effects are really just refraction in action. Are there like formal rules or laws that describe this precisely? How much does it bend?
Yes, there are two main laws of refraction. The first one is mostly about geometry.
Okay.
It just says that the incoming ray, incident ray, the normal line, and the bent ray, refracted ray, all lie on the same flat surface, the same plane.
Like they could all be drawn on one sheet of paper.
Exactly. Keeps things organized.
And the second law, is that the more mathematical one?
That's the one. It's called Snell's law. It's really fundamental. It says that for any two specific materials like air and water, and for a particular color of light.
Oh, color matters. We'll get to that, I guess.
Yes, it does. But for now, let's just say for a given pair of media and light color, the ratio of on the sine of the angle of incidence, sin I, to the sine of the angle of refraction, sin R, is always constant.
Sin I divided by sin R equals a constant number.
Exactly. Sin I, sin R equals constant. And that constant value is called the refractive index of the second medium relative to the first. We often use the Greek letter mu, sin, for it.
Mu, the refractive index. So that number tells you how much bending happens between those two materials.
Precisely. It's like a measure of the bending power of the second material compared to the first. Different materials have different refractive indices. Water's index relative to air is about 1.33. Glass is typically around 1.5.
So Snell's law lets you calculate the exact angle R if you know I and the materials involved.
Yes, it's incredibly powerful. It's the basis for designing lenses in glasses, cameras, telescopes, anything that manipulates light.
Wow. Okay, so refractive index is key. What happens when light goes through, say, a block of glass, like a rectangular slab?
The glass slab experiment. Classic. Okay, so light hits the first surface, air to glass, rarer to denser.
It bends towards the normal.
Right. Then it travels through the glass and hits the second surface, glass back to air, denser to rarer.
So it bends away from the normal this time.
Correct. Now, the interesting thing is if the two sides of the slab are parallel, the amount it bends away when leaving is perfectly related to how much it bent towards when entering. Meaning the ray that comes out, the emergent ray, is actually parallel to the original ray that went in, the incident ray.
No way. So it doesn't change the light's overall direction?
Not its direction, no. The angle it comes out at, the angle of emergence D, is exactly equal to the angle it went in at. But the ray is shifted sideways.
Ah, okay.
Yeah.
So parallel but offset. Like it took a little sidestep through the glass?
That's a perfect way to put it, a lateral displacement.
Okay. What about a different shape, like a prism, a triangular block? That must be different.
Oh yeah, a prism behaves quite differently. Because the sides aren't parallel, the light doesn't come out parallel to its original path. It gets deviated.
Deviated. Changes direction.
Yes. When light enters the prism, say from air to glass, it bends towards the normal. Because of the prism shape, this usually means bending somewhat towards the thicker part, the base of the triangle.
Okay, towards the base.
Then when it leaves the other side of the prism, glass back to air, it bends away from the normal. And again, due to the geometry, this also tends to bend the ray further towards the base.
So it bends toward the base going in and bends towards the base coming out. Sort of.
Essentially, yes. The net effect is that the light ray is deflected, its final direction is different from its initial direction, and it's deviated towards the base of the prism.
And we can measure that change in direction.
Absolutely. The angle between the original direction and the final direction is called the angle of deviation, often labeled D.
Angle D. And there are other angles too, right? Like the angle of the prism itself.
Yes. There's the angle of incidence I where it enters, the angle of refraction R1 just inside. Then it hits the second face at an angle R2 and emerges at an angle E. And the angle at the top of the prism triangle is the angle of the prism A.
Lots of angles. Is there a relationship between them?
There is. A useful one is that the angle of incidence plus the angle of emergence equals the angle of the prism plus the angle of deviation. So I plus E plus D.
I plus E plus A plus D.
Mm-hmm.
Okay. I think I remember reading about something called minimum deviation. What's that?
Right. If you shine light through a prism and change the angle E that it goes in at, the angle of deviation D also changes.
How so?
Well, as you increase I from a small value, the deviation d first decreases, then it hits the lowest possible value, and then it starts increasing again.
So there's a minimum point for the bend.
Exactly. That minimum value is the angle of minimum deviation, DMD, and something special happens right at that point.
What's that?
At minimum deviation, the path of the light inside the prism is symmetrical. The angle of incidence E equals the angle of emergence E, and the two angles inside, R1 and R2, are also equal. The light ray inside travels parallel to the base of the prism.
Parallel to the base. Okay. Is that minimum deviation useful?
Very much so, especially for measuring the properties of the prism material, like its refractive index, very accurately. It's used in instruments called spectrometers.
And what affects that minimum deviation angle? What makes it change?
Good question. Four main things. First, the angle of the prism A. A bigger prism angle usually means more deviation.
Okay.
Second, the material the prism is made of, specifically its refractive index. Higher index, more bending, more deviation.
Makes sense.
Third, somewhat obviously, the angle of incidence I. You have to set I just right to get that minimum D. And fourth, the color or wavelength of the light itself.
Back to the color thing. Okay, this sounds like it leads directly into dispersion, Newton's big discovery.
Exactly. Sir Isaac Newton did a famous experiment. He took a prism and let a thin beam of sunlight pass through it.
And instead of just bending, it spread out.
It spread out into a beautiful band of colors, just like a rainbow. Violet, indigo, blue, green, yellow, orange, red.
VBGYOR.
VBGYR, right. And the crucial insight was that the prism wasn't making the colors, was it?
No, not at all. That was the genius of it. Newton realized that white light, like sunlight, isn't pure. It's actually a mixture, a combination of all those different colors of light.
So the prism just sorts them.
Precisely. It acts as a sorter. And why can it sort them? Because, as we hinted, the refractive index of glass, its bendiness, isn't exactly the same for all colors.
Oh, so different colors bend by different amounts.
Yes. It turns out that violet light travels the slowest through glass. Because it's slowest, it has the highest refractive index, and so it bends the most.
Violet bends most.
Red light travels the fastest through the glass, so it has the lowest refractive index, and it bends the least.
Red bends least. And all the other colors, indigo, blue, green, yellow, orange, they fall in between, bending by intermediate amounts. So the prism fans them out, separates them by angle, creating the spectrum. This phenomenon is called dispersion.
Dispersion. The splitting of white light into colors because different colors bend differently. Wow. And is that how rainbows work?
That's exactly how rainbows work.
Yeah.
Each individual raindrop acts like a tiny prism.
Seriously? A spherical drop?
Yep. Sunlight enters a raindrop, it refracts and disperses splits into colors just inside the front surface. Then those colors travel to the back of the raindrop, reflect off the inside back surface.
Like a mirror?
Sort of an internal reflection.
Oh.
Then they travel back to the front surface and refract again as they exit the drop back into the air, heading towards your eye.
So there's refraction, dispersion, reflection, then more refraction.
That's the sequence.
Yeah.
And that whole process spreads the colors out. Because red light bends the least overall, it appears on the top or outer edge of the rainbow arc. Violet bends the most, so it's on the bottom, the inner edge.
That is absolutely amazing. Billions of tiny raindrops all doing that complex dance with light.
It really is quite incredible. Nature's own light show.
So the prism just splits the light. Newton also showed you could put the colors back together, right?
He did. He used a second prism, identical to the first but flying upside down, and placed it in the path of the dispersed colors.
Yeah.
And the second prism recombined all the colors back into a beam of white light, proving conclusively that white light was made of those colors.
Clever. Okay, so we have refraction bending and dispersion splitting by color. Any, practical uses for these effects we see every day, besides explaining rainbows and bent straws?
Oh, absolutely. Refraction is the bedrock of optics. Eyeglasses work by using carefully shaped lenses to refract light and correct vision problems, focusing light properly on your retina.
Right, lenses rely on refraction.
Cameras, microscopes, telescopes all use lenses or combinations of lenses designed using the principles of refraction to form images, magnify things, or gather faint light.
And what about dispersion? Any applications there, or is it just pretty?
Dispersion is sometimes a problem in lenses. It can cause color fringing, but understanding it helps design better lenses. And it has direct uses, too. Think about why danger signals, stop signs, brake lights are red.
Why are they always red?
Well, remember, red light bends the least. It also turns out that red light, having the longest wavelength, scatters the least as it travels through the air, especially through haze or fog.
Scatters least, meaning it travels straighter, further.
Essentially, yes. It's less likely to be bounced off course by tiny particles in the air. So, red light from a signal has the best chance of reaching your eye over long distances, or in poor visibility. That's why it's used for warnings.
That makes perfect sense. Wow. And didn't Newton also have some kind of spinning color disk?
Yes, Newton's color disk. He painted segments of a disk with the 7 colors of the spectrum, V, I, B, G, Y, or, in the right proportions.
And when he spun it really fast.
When spun rapidly, the colors blur together in your eye, and your brain perceives the disk as being white, or maybe a grayish white. It was another way to demonstrate the recombination of colors.
Fascinating. Okay, let's try and wrap this up. So the big takeaways from this deep dive. Light bends. That's refraction, when it goes from one clear thing to another because its speed changes.
Right. And how much it bends depends on the materials, their refractive indices, and the angle it hits at, governed by Snell's law.
And white light isn't simple. It's a mix of all the colors of the rainbow.
Exactly. And those colors can be split apart, dispersed by something like a prism, because each color bends by a slightly different amount. Violet the most, red the least.
Leading to phenomena like rainbows and explaining why red is used for signals. We got some real aha moments there, I think.
Hopefully. It really shows how these fundamental ideas about light explain so much of what we see, from the mundane to the spectacular.
Definitely. It's amazing how just light-changing speed causes all this. Okay, so final thought for you, the listener, to chew on. Think about all the clear stuff around you. Water, windows, maybe eyeglass lenses, plastic bottles.
Light is constantly passing through them, bending, refracting, shaping how you see the world.
So, beyond the bent straw or the rainbow, what other everyday things might be explained by this? Maybe the shimmering heat haze you see over a hot road in summer?
Or the way things look bigger when you see them underwater through goggles.
Could refraction be involved there too? This deep dive feels like just scratching the surface of how light really works, doesn't it?
It really does. The dance of light is incredibly intricate and beautiful.